Hello everyone, welcome to another session of Coffee O'Clock. I am your host Akash Kundu and I'm a PhD student at Polish Academy of Science. And today, as you see, we have as a guest speaker Suhail Ahmad rather, and to give a small introduction about him, he did his master's from University of Kashmir, and after that he joined IIT Madras, Indian Institute of Technology Madras, as a senior research fellow under supervision of Professor Arul Lakshminarayan. And as some of you might know that Arul Lakshminarayan professor is one of the pioneers in the field of quantum chaos. So as usual, that Suhail in his PhD did quantum information theory, many body physics, and also quantum chaos, obviously, because he was with Professor Arul Lakshminarayan. Currently, Suhail is a postdoctoral fellow at the Max Planck Institute for Physics of Complex Systems, and he's going to talk about today a very interesting problem like Euler 36 officers problem, and it was unsolved for more than 250 years, and today Suhail has a solution, quantum solution, and he's going to talk about it. So we are really excited that Suhail is here, and thank you everyone for patiently waiting. So Suhail, the stage is all yours.
Thank you very much, Akash, for a kind introduction, and all others for joining us and for their patience. So first of all, thank you very much for joining. As Akash mentioned, I'll be talking about something which has to do with, something which is quantum and which will be related to these interesting combinatorial designs and all. So, as Akash had sort of warned me, and in the beginning when we communicated, he said that it will be a very broad audience. So keeping in mind the broad audience, and I believe that there will be some high school students also joining us on YouTube or on Zoom. So what I have tried to, prepare this talk is, first I'll give a very sort of an introduction to combinatorial arrangements, which I believe all of us have come across at some point, either in newspapers or in some recreational mathematics or something. Okay, so I'll first give a general introduction to these Sudoku type combinatorial arrangements. Don't worry about these different terms over here, Latin squares, orthogonality and all, and we'll see this 36 officers problem, how it arises. Second thing, I'll keeping in mind that there will be people from different backgrounds, I'll give some, whatever I can do, some basic notion of entanglement in quantum systems and all. Then we'll put, as you can see, I have highlighted this quantum everywhere. So in the first part, wherever you have these combinatorial arrangements, I just define the quantum analogous of this, and then we'll define the solution to this 36 officers problem in the quantum case. And the way I'll introduce these things, at the end of my talk, I'll give the more technical details of the talk as I was told. So let's first start with a very, simple game which we have come across in maybe in newspapers and all. It's called the Sudoku, where you see there on the left-hand side there is an 9x9 arrangement, and there are some numbers filled in these squares. These are called clues, like you have 5, 3, 7 in the first row, and finding a solution to this Sudoku means that you have to fill in these empty boxes or squares, such that in any row along this row or any column, you should have numbers from 1 to 9. That means there should be repetitions not along any row or any column. And there is an additional constraint that if you take this 3x3 square over here, that means this 3x3 square over here, that's why it is shown in bold over here, such that you should have numbers from 1 to 9 in these 3x3 squares also. So there are 3 constraints to be satisfied. First one, there should be no repetition along the row. There should be no repetition along the column, any row or any column. And in each 3x3 block, there are 9 3x3 blocks shown over here. There should be no repetition of numbers. And shown over here on the right hand side is a solution to this 9 by 9 Sudoku. Okay, you can see, you can check, it's one of those things where finding a solution is very difficult, but once you find it, you can check it very clear. Okay, like this NP hardness thing and all. Anyway, so you can check that in any row and any column, there are no repetitions, and in each 3 by 3 block, there are numbers from 1 to 9. So this is, I believe that most of us have come across such games in somewhere. But what we are going to do in this, I mean, which is relevant for the purposes of this talk, are somewhat simpler constraints like what is shown over here. And you can see we have a 9 by 9 square. So we want to kind of build up from simpler objects and try to impose these constraints, similar constraints, and look at those objects. And the question I ask is the following. Suppose I have 4 cards, okay? I have 4 cards, and these 4 cards have 2 different ranks like ace and king, and 2 different suits, that is diamond and spades, which are shown over here. Ace of diamonds, king of diamonds, ace of spades, and king of spades. These are 4 different cards shown over here. And I ask whether these 4 cards can be arranged in such a way, in a 2 by 2 arrangement, such that along any row, I should not have a card with repetitions. You can see on the left-hand side, there is an ace of diamond. You cannot put ace of spades over here because ace will be repeated. So I have to put king of spades. This card I have to put over here. Now, to the second row. In the second row, we have to choose the other 2 cards. If I choose, for example, king of diamonds, let's say, so that this is not repeated, but you can see the suit is now repeated. Similarly, if you put ace of spades over here, then the ace will be repeated. And the question which I asked, it is sort of not a good idea to start with a negative solution, but in the 2 by 2 case, you cannot find a solution to this problem. That if you have 4 cards, there is no way to arrange these 4 cards in a 2 by 2 arrangement such that you don't have repetitions of ranks and these suits. Okay, so it's a bit negative. Let's try to do it not in a 2 by 2, but 3 by 3 case. So 3 by 3 case, there will be 9 cards coming from 3 different suits. So I'll have ace, king, and queen, and 3 different suits, diamond, spades, and flower. And the cards are shown over here. So you can see there are 9 different cards over here. And what I want is a 3 by 3 arrangement such that the ace, such that the rank and suit are not replaced. And shown on the right-hand side is such an arrangement. You can see that along the first row, there is an ace of diamond. Ace is not repeated. Diamond is not repeated. Similarly, the other ranks and suits are not repeated. And you can see that in all 3 columns and all 3 rows, the rank and suits are not repeated. The arrangement, such arrangements, this for 9 cards, you can find an arrangement for these 9 different cards such that you don't have repetitions of ranks and suits. So such arrangements are called orthogonal Latin squares. So such an arrangement is called an orthogonal Latin square. And to understand the structure of these orthogonal Latin squares, so what we have over here is first an arrangement at 3 by 3 arrangement shown on the right hand side, 3 by 3 arrangement of these ranks of cards. So we have ace, king, and queen. It does not repeat along any row and any column. We call it a Latin square. And similarly, we have a Latin square of suits, such that if you superimpose them, you get an arrangement on the right hand side. So these Latin squares are called orthogonal if the superposition of them gives you d square, or in general d square, but over here you get 9 different pairs. Okay, so all different pairs, all pairs you obtain over here are different. So let's see the formal definition. We see 2 Latin squares L1 and L2 of size d are said to be orthogonal, denoted as let's say like this, if superimposing them together results in d square different pairs. So in general, you will have d square cards and you have to arrange them in these d by d arrangements. In general, you have a square arrangement of d square cards. And the terminology is sometimes called the L1 is called an orthogonal mate of L2 if both of them form this orthogonal Latin, if both of them form orthogonal Latin squares and vice versa. Okay. So shown over here are orthogonal Latin squares of size 3. So two Latin squares, these orthogonal Latin squares does not exist. Let's try to see more these orthogonal Latin squares. So shown over here are Latin square of size 4, Latin square of size 4, and if I superimpose them, I get an arrangement on the right hand side, which is an orthogonal Latin square, which are orthogonal Latin squares of size 4. Okay. So 16 cards also we can do. Now the question we ask now, for what dimension D do OLS, so I'll define this as OLS of D, means orthogonal Latin squares of size D. So the natural question now it arises, so it exists for 2, it exists for 3. I just showed, sorry, it does not exist for 2, 3 and 4, it exists. Now one would like to ask for what dimensions these orthogonal Latin squares exist. And this question was first, studied by Euler in a very, it was asked as a puzzle to Euler, and it has an interesting history, as I have mentioned it over here, which dates back to the 18th century. And the Euler became interested in these, what we now called orthogonal Latin squares, because of this 36 officers problem. That was the 36 officers problem, appears in my title also. The question, it was sort of a puzzle which was asked to Euler was the following. 6 different regiments have 6 officers each, 6 officers, each one belonging to different ranks. Can these officers be arranged in square formations so that each row and column contains 1 officer of each rank and 1 of each regiment? So in terms of these cards, Euler was asked to find an arrangement of 36 cards, like shown over here for 16 cards. Find an arrangement of 36 cards. Over here, we are talking about rank and suit, but over here they are talking about rank, regiment and rank. It doesn't matter. So 2 properties, regiment and rank. You have to find such an arrangement such that there should be no repetition of rank and no repetition of regiment in any row or column. So in the terminology which I just described, the solution to this 36 officers problem is equivalent to finding an orthogonal Latin square of size 6. Okay, so solving this problem is equivalent to finding an 6 by 6, finding an OLS of 6. That means you have to find a 6 Latin squares such that if you superimpose them, you should get 36 cards on the right hand side. And Euler tried in 1779, he tried to find orthogonal Latin squares for all odd dimensions. He was able to find, like the one I showed for D equal to 3, and it was sort of an easier, I would say, easier way to construct orthogonal Latin squares for all odd dimensions, okay, shown in the green over here. And also he was able to find orthogonal Latin squares for these for dimensions which are divisible by 4. 0 mod D, that means all of them are divisible by 4. 4, 8, 12, 16, 20, 24. D equal to 2, as we just, as I described in my first slide, D equal to 2, it does not exist. The next sort of non-trivial case was D equal to 6. So D equal to 6 on the right hand side, it is written as D equal to 2 mod 4. That means it is of the form 4n plus 2. So D equal to 2, it's not D equal to 2, it's not Akash, but can you hear me clearly?
Yeah, I can hear you clearly. Yeah.
Okay.
And I have a question. Can I ask right now? Or?
Oh, sure. Please go ahead. Sorry, there are some questions in the chat. Sorry for missing them. Is there a unique solution? No. Akash, please go ahead. You can have your question, then I'll answer.
Yeah, I have a lemon type question probably, because I was thinking that if you don't have like equal number of ranks and equal number of positions, then what would happen?
Oh, okay. That's an interesting question. So if you don't have an equal number of ranks and equal number of regiments, then what happens is you can have repetitions, right?
Yeah.
You can have repetitions. Then there is some known combinatorial objects called frequency squares, or in general, you can have a Latin rectangle where you can allow repetitions of that. And actually, you can find a solution when you allow the repetitions.
Okay, and because I was thinking that consider there is like 4 by 3 or something, like not like 4 by 4, then because in the 4 by 3 you have 3 by 3, right? So can you say that it is locally this OLS, orthogonal lattice square or something? Because
I mean, the kind of objects which I am aware of, when you allow the repetitions, like the cases which you are saying, are studied under these frequency squares. And there is a general definition: when you don't have a square arrangement, you have an Latin arrangement. It's called a Latin rectangle, as I can recall. It's called a Latin rectangle. Yeah. There was a question in the chat: is this solution unique? For example, I'm not able to go back. Okay, these arrangements which I showed over here, no, I mean, is this a unique way to find an orthogonal Latin square? The answer is no. And as if I recall correctly, there are 72 orthogonal Latin squares of size 3. Okay, so there are 72 arrangements in which you can 72 arrangements which are orthogonal in some sense. Okay, so it's not unique. Similarly, for d equal to 4, I think the number is nice. That's why I remember it is 3, 4, 5, 6. I guess arrangements are there which are orthogonal Latin squares. Okay, so Euler was able to find for these the cases which were remaining were 2 mod 4. That means for dimensions of the form 4n plus 2, like 2, 6, 10, 14, 18, 22, so on and so forth. And he conjectured, he tried for d equal to 6 and all, he could not find. And while he could find for all other dimensions, he conjectured that there are no solutions for d equal to 4n plus 2. This was a conjecture. And in fact, in 1900, so 1770, after 121 years, Gaston Parry actually exhaustively proved that, I think this is not clear, but he showed exhaustively for d equal to 6, it actually does not exist. So that takes care of these two. Now comes the year 1959. These two statisticians, I think they were working at ISI Kolkata, R.C. Bose and S.S. Srikande. They found orthogonal Latin squares of size 22 first in 1959. And with Parker, d equal to 22 and d equal to 10. And with E.T. Parker, they showed that the orthogonal Latin squares exist for all dimensions, except only for d equal to 2 and 6, which is very, very surprising. And this answer was, it started with 1779. Then in 1901, it was shown for d equal to 6, it does not exist. We had to wait until 1959 to wait for this answer that orthogonal Latin squares exist for all dimension d except for d equal to 2 and 6. And in fact, after this, they featured in the New York Times, and the title you can see over here is "Major Mathematical Conjecture Propounded 177 Years Ago is Disproved." So this completed the existence of, about the existence of orthogonal Latin squares, that these exist for all dimensions except for 2 and 6. Okay. Now I'll now go slightly into, so this was what I wanted to say about orthogonal Latin squares.
Hi, Suhail. Really enjoying the talk. I just want to ask you if you can say something about the proof of 6. Like you said something about the proof of 2. Just like some words about, maybe it's not trivial, but what are things used?
Yeah, the thing is, actually d equal to 6 is a very non-trivial. The proof is very non-trivial. I mean, the For example, the Gaston-Tarry's proof is sort of exhaustive thing, but it actually goes into this discrete mathematics and all. Of course, from over here, you can see that there is no, a lot of number theory happening over here. And 6 is, you can see 6 is the first number, which is not odd and which is not a power of prime, right? That you can see from the number theory. And
Wait, it's not odd and it's not what?
It's not a power of prime. Once you have a power of prime, like 4, for example, 4, although it is composite number, but it's not power of prime. So it's like that, I guess it's called a perfect number. I guess 6 is the smallest perfect number. And regarding the proof, actually, it's very non-trivial. And the proof I am actually aware of is some, this is a shorter proof in 1980s. It's based on some graph theory and all. And I'll be happy to talk about, to share the references and all after the talk. But it's actually, to be honest, it is highly non-trivial that it does not exist for d equal to 6. Of course, nowadays people just ask me, what is so about a d equal to 6? You run some powerful computer and you can do it exhaustively. But you can just see doing it in 1901 exhaustively. It's very a very commendable task. So yeah.
Okay,
there's no, to be honest, there is no simple way to convince that for d equal to 6 it does not exist. So the only proof I am actually aware was in 1980 by some mathematician based on some graph theory, theoretic arguments.
Okay.
Yeah, thanks for the question actually. So since I will be doing some quantum stuff, let me just give some short, very basic thing. I'm really sorry for the experts in the audience, as I believe that there are some high school students, so these couple of slides are for them. So excuse me for that. So the quantum theory, as we know, the world around us mostly governed by the classical mechanics based on Newton's laws, Kepler's laws, and so on and so forth. So classical mechanics to a very good accuracy describes most of the phenomena ranging from maybe apple falling on Newton, rockets, planetary motion, and all are described by the classical mechanics. The description of the microscopic world, that means the phenomena which are happening at the subatomic and atomic levels, are described by the quantum theory. They're no longer described by the classical mechanics. And most of the phenomena which happen at the microscopic scales are very counterintuitive. They're very different than the kind of things or phenomena which are which we are sort of observing in our day-to-day life. And to sort of set the stage, I'll start with the simplest quantum system, which is called a quantum bit or qubit. Okay, so a quantum bit or qubit is a two-dimensional, is a quantum system with two distinguishable or orthogonal states, which I'll represent by 1 and 2 in the rest of the talk. So it's different than the usual, than we do usually in quantum information. We start with 0 and 1, but I'll use this notation. So these are two distinguishable states, two-level systems. That's why we have these column vectors of size, column vectors of size 2. Two rows are there. So because it's a two-dimensional system, and these are two orthogonal states. And this is qubit is more like an abstract sort of abstract notion and all. You can think of physical realizations are like a two-level atom. For example, a spin-half electron serves as a qubit in, for example, in all these quantum computing platforms and all. Also the polarization states of photon, is a physical realization of a qubit. And one of the, as I was just mentioning in the previous slide, one of the weird or very counterintuitive things happening in at the subatomic level, if, for example, these are two possible states of a qubit, 1 and 2, then a most general state of a qubit is given by this, where this A times ket 1 plus A2 times ket 2. okay, which is a linear superposition of these states where these AIs are in general complex and they satisfy this normalization constraint. So this is a very peculiar thing to quantum mechanics, is that there is a what's called superposition of these basis states, and the general state of a qubit is given by this. And I think most of us, or those who are not from the, who are not from the, quantum information field, working in quantum information field, might have come across with this sort of dilemma of the Schrödinger's cat, where the cat is simultaneously in two states of being alive and dead over here. And in these cases, these A1s, A1 and A2 are real, and they're both equal to 1 over square root 2. So there is intrinsic probabilistic probabilities built in the quantum mechanics, in the sense that if you observe such a state, for example, given a qubit in this superposition of 1 and 2 states with these amplitudes, A1 and A2, if you observe such a state, you're going to get measurement out you'll collapse to this state, taking some interpretation, collapse to this state where you'll get one state with probability given by this overlap, which is given by modulus of A1 square and the modulus of A2 square. So the only thing I wanted to say over here, these probabilities are given by the modulus squares of these amplitudes, okay, which will be useful for us for our later discussion. Also, for example, over here, P1 and P2 are both equal to half. So it is equally likely in one of these two states. And to make it more weirder, one of the weird things which happens in quantum systems is the quantum entanglement. And it was known from the early days of quantum mechanics. I've just taken this code from Erwin Schrödinger in 1935. And what is written in this code, maybe I'll just write it in these equations. And he describes what's called this quantum entanglement as a property of composite quantum systems, in the following sense, that if you have two quantum systems, for example, I have labeled them A and B, and they are far apart, they don't know each other and all, such that you can describe the state of these two these two particles. They can be qubits or something. You can ascribe a state to A as psi1 and ascribe a state to B as psi2. Such a state will be called an unentangled or product state. Okay, so this is when they don't know each other. And then what happens, they start to do some temporary physical interaction, as is written over here. Some interaction happens for some time, and then they leave again. The thing is, when they interact non-trivially, what happens generally is that the final state cannot be written in this product form. So this psi initial was over here, now it becomes, now the state describing this composite quantum system, which is denoted by psi f. You cannot write it in a product form in the sense that you'll say the state of this is this, state of this is this. State of A is psi, state of B is phi. Such a state which cannot be written in this product form is called an entangled state. Okay. It's a very counterintuitive thing, and as Schrödinger mentions over here, it's the characteristic trait of quantum mechanics is the one that enforces its entire departure from classical lines of thought. By the interaction, the two representatives or psi functions have become entangled. Okay, so I think this is the first usage of the word entanglement. It's due to Schrödinger. Let me just not go into the details, but let me give an example of an entangled state. And as I was saying, the entanglement is a property it's a property. Akash, by the way, how much time do I have?
You have something like half an hour.
Oh, I have half an hour. Okay, thank you very much. Thanks. Let me just give an example of an entangled state. As I was saying, it's a property, entanglement is a property of composite system. That means I need to have two quantum systems. And the simplest quantum systems, composite system I can take is that of 2 qubits. So I have 2 qubits, these 2 qubits, and the state of these 2 qubits A and B is given by this 1 over square root 2 of, so the first, this is A, B, 1, 1 plus 2A, 2B, okay. Such a state you cannot write as something which is such that you can ascribe a state to qubit A and qubit B. And in fact, if you calculate the what's called a reduced density matrix, or the state corresponding to the individual systems like A and B, what you will find is actually a maximally mixed state. It's equal to identity divided by 2. Okay, so it's not a pure state, it's a mixed state now, in the sense that if you look at, so what happens is the following in an entangled state. So I'm talking only about the entanglement in pure states over here. So you have a complete description of 2 qubits, which is given in this equation, psi AB. Now, if you look at the state of the individual qubit, it's no longer pure state. That means you can no longer ascribe a state to an individual qubit. That means the information about the whole is known, but if you look at the constituents or the constituents which form this compound system, they no longer are in definite states. Okay, so you don't get any information by looking at the individual spins. They're all maximally mixed. They're in an equal superposition of these basis states. And what do we get from this? Is actually which has I mean a lot of discussions. This as you can see, this state is called the Bell state, or the EPR pair, Einstein, Podolsky, and Rosen. And this state was, I think, shown in some sense to kind of argue or counter the thing that the quantum mechanics is not complete and all by these 3 gentlemen. But what do we get from this entangled state is the following. If you have an entangled state shared between A and B, so let's say A is on Earth or maybe in Europe and B is in India, and there is an entangled state shared between these two of this form. Okay, so qubit A is in over here and qubit B is in some distant location, doesn't matter. And this share such a state. Now the qubit A is measured and some random outcome is happening that is proportional to this amplitude. It can be it can be equally either 1 or 2. Okay, you get one of the outcomes. The thing is, if you get a random outcome, one of the random outcomes, suppose you get 1, then it automatically tells you that you can the state of the other party or the state of qubit B is 1. So it is perfectly correlated. Similarly, if the random outcome gives you state 2, then the state of the other qubit is also 2. So it leads to these correlations, and these correlations cannot be described by any classical model as was sort of put into this concrete form in terms of Bell inequalities by John Bell in 1965, that the correlations which arise from quantum entanglement cannot be described by any what's called in this classical hidden variable model and all. Let me not go into these details, but just to mention that the correlations and all about the quantum entanglement, you might have many of you who are not in the field might have come across this that the Nobel Prize in physics in 2022 was actually jointly awarded to Alain Aspect, Clauser, and Zeilinger. And you can see it was for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Okay, so it was really, I mean, the last year's Nobel Prize were really devoted to the understanding of the entanglement at the, I mean, experimental level and all. And using now the entanglement as I'll briefly mention, it's like the resource in the all the quantum information protocols, as we will as I'll briefly mention. Okay, so it acts as a resource like the energy in the quantum information protocols. Okay, so I have now briefly mention what entanglement is. And let's try to merge the first two sections which I have introduced right now. So what I will do now is I'll do some mappings from these. I'll go from discrete symbols. So shown over here is a discrete symbol 1. I map it to a quantum state or a vector, let's say, okay, a vector which is represented over here. And two different symbols will be mapped to orthogonal states over here. Okay, so one goes to ket1, 2 goes to ket2, such that if these I and j are different, this will be delta ij. I mean, they will be orthogonal. Okay, so different discrete symbols will be mapped to orthogonal quantum states. Okay, and I'll not only talk about in the rest of my talk about qubits, but I'll be talking about qubits. So a qubit is a higher dimensional generalization of a qubit with distinguishable states from 1 to d. So ket1, ket2 up to ket d. So you can think of this as a d-level system in general. Okay, and I have mentioned on this slide also, I have on the left-hand side, what I was talking about in the beginning of my talk was in some sense classical combinatorics, where I had symbols like 1, 2 up to d. Then I had orthogonal Latin, I have Latin squares, and then I had notion of orthogonality. Okay, I had some different symbols in each row and column and all. There was no sort of entanglement such in classical case. And the way these sort of symbols are manipulated is using the discrete permutation group, but don't worry about this, as I didn't say much about this. On the other hand, in quantum combinatorics, what I have is, so I go from here to here by vectors. So I'll be talking about vectors, and I'll define a notion of, for Latin square, there will be a QLS, means quantum Latin square. Similarly for orthogonal Latin squares. So when I was seeing different symbols over here, these map to orthogonal vectors or orthogonal quantum states over here. And over here, what I have now is, in some sense, the freedom of superposition. I can take a superposition of 1 and 2 or any states. And most importantly, I'll have entanglement also between these. When I'll have composition, I'll have entanglement also. So this, in some sense, over here, there is discrete permutation group. Over here, the way these sort of states are transformed is using the continuous unitary group, elements from the continuous unitary group. Okay, so let me just sort of connect it to the previous discussion in the first part of my talk, where I had orthogonal Latin square. So it is sort of convenient for me to think in terms of symbols now rather than in terms of cards. So I have orthogonal Latin squares of these numbers from 1 to 3. So this is an orthogonal Latin square of size 3. This is a Latin square of size 3. This is a Latin square of size 3. And you can see that in any row or any column, you don't have repetitions. You superimpose them, you get an orthogonal Latin square on the right-hand side. So now what I do is I just translate each of these symbols into a ket. Okay, now I translate into a three-dimensional vector. So where these will be the basis status for a 3-level system or a qubit. Okay, ket1, ket2, ket3 will be the distinguishable states corresponding to a qubit. And these arrangements, as you can see, if I take any row over here, the fact that we started with different symbols translates into 3 different orthogonal vectors. That means each row or each column over here and also in this Latin square forms an orthonormal basis in d-dimensional vector space. Okay, so each row or each column of these form an orthonormal basis in a d-dimensional space. So I'll call it an quantum Latin square. Okay, I'm sorry about I hadn't included the reference over here. I hope I'll talk about it in the later. So this idea was actually introduced by Jamie Ukari and Benjamin Musto, I guess. Yeah. As early as 2017. So these form an orthonormal basis along any row and any column. And on the right-hand side, what I have is actually, so these are single particle states or single qubit states. But on the right-hand side, as you can see, I now have two particle or two qubit states, and all of them, because these were all these pairs were different because of the property of the orthogonal Latin square. All these states on the right hand side are actually orthogonal states. That means they are orthonormal, and this gives the concept of orthogonality of quantum Latin squares. That means two quantum Latin squares are said to be orthogonal if together they form an orthonormal basis in this doublet Hilbert space. Okay, so D tensor CD. Okay, okay. Thank you very much, Akash. Thanks for the reference. Okay. So two quantum Latin squares will be called orthogonal if together they form an orthonormal basis in this doublet space. Okay. Now, what it has to do all with, I mean, what I was saying. The thing is, once you have an orthogonal Latin square, you can construct a four-party state out of it, the state of four qubits. Okay. How? The following. You start with an orthogonal Latin square, this one, okay, Latin square, sorry for going back and forth, this Latin square, orthogonal Latin square, sorry for messing this Latin square and orthogonal Latin square. So I start with an orthogonal Latin square, this one. Not only do I need this, but I also write the first pair is the address of the corresponding OLS entry. That means this is 1, 1, then you have 1, 2, then you have 1, 3. Okay, first row, third column. Similarly, you have 2, 1, 2, 2, and 2, 3. Okay, and similarly, you have 3, 1, 3, 2, and 3, 3. The third and fourth entry are all from the orthogonal Latin squares. The entries are over here. Now, what I do is I construct a state of four particles. You can see now this is a state of four three-level systems because you have symbols from 1 to 3. If you start from a d by d orthogonal Latin square, then you will have a state of four qubits. Okay, so this is the state shown on the right hand side is a state of four qubits. Okay, and what's important for all the discussions which I had was if I look at the reduced density matrix of two particles, that means I have four particles, 1, 2, 3, 4 shown over here. If I trace out 3 and 4, trace out 3 and 4 means I focus on the state of any two, the first two of them. Okay, I trace out the rest. What I get is actually a maximally mixed state. I get an identity. And similarly, if I take, it does not matter whether I take 1, 2. If I take 1, 3, I still get maximally mixed state. If I take 2, 3, those are the only three cases. So you have 1, 2 with 3, 4, 1, 3 with 2, 4, and 2, 3 with 1, 4. These three possible reductions are there, or partitions are there. And what we found is actually all three these reduced density matrices are maximally mixed. You might ask me, why are you taking two particle reduced density matrices? Because if I take one particle reduced density matrix, that will also be automatically maximally mixed. And what I am interested in, the kind of things which will be useful for later discussions are these maximally entangled states. That means if you take any half of the system, you should have the state should be maximally, the reduced density matrix should be maximally mixed. So in some sense, these will be the generalizations or higher generalizations in terms of, for example, local dimension, the dimension in terms of number of parties also of the Bell state. So generalizations of Bell states in the sense that if you take the reduced density matrix of any half of the system, it should be maximally mixed. So that's why I'm taking, because I have four particles, I have to trace two of them. And such states are called absolutely maximally entangled states. Okay, so an absolutely maximally entangled state denoted as AME of n comma d, if you trace out any half of the particles, the state of the this rest is proportional to identity. And these absolutely, since Maybe I should have given some more motivation. The motivation for studying such highly correlated states is these are highly entangled states comes from because they have a correspondence with error correcting codes, okay, which was found in this paper by Scott. They're related to these pure error correcting codes, which is very crucial for scalable quantum computing and all that stuff. They are useful for parallel teleportation. They will be useful for quantum secret sharing, and they will be used. They're also useful in these holographic codes or the models of quantum gravity and all. So, are there any questions as of now?
I have a quick question.
Sure.
So in the state, so thanks. Actually, this is quite clear. And then, so in the state that you mentioned, but if I take something like row 1,4, right, I also get the identity. Is that right?
That's true.
So is this like, are these just examples that you give, or is it like if you take any combination?
If you take any, so row 1,4 I don't calculate because row 2, 3 being maximally mixed means that row 1,4 is maximally mixed.
Ah, okay. That makes sense.
Yeah, because
right. Okay. Thank you for that.
Yeah, welcome. So these are the only three two-particle reduced density matrices. So, and they have quite wide applications, as I was saying. These and these states are highly correlated states, and that makes them useful for all these. Error correcting codes, secret sharing, the parallel teleportation, and all. And for example, let me just mention in the usual teleportation protocol, what actually is used is a maximally entangled state of 2 qubits. Okay. You can use a maximally entangled state of 2 qubits and some 2 bits of classical information to teleport a state from A to B. And you have to use that maximal entanglement. If you don't start with a maximally entangled state, you're not definitely going to get, you cannot teleport the state with 100% fidelity then. So, let me just, these are, so.
Oh, sorry, I think Sriram had a question. His hand is up.
Sure.
So why should the definition of AME have the size of set S is less than N over 2? Like, okay. So say in the 3 qubit case, right, when Q12 is proportional to I9,
U12 cannot be proportional to I9.
Row 12 is proportional to I9. Row 3 is also, you said, maximally mixed.
No, for a 3 qubit state, row 1, 2 cannot be proportional for 3 qubits, cannot be proportional to identity by 9. Because that will mean that, because you have to think in terms of the spectrum of the reduced density matrix, that means when you are saying row 1, 3 is proportional to I by 9, that means the eigenvalues of the reduced density matrix are all equal to 1 by 9. That means those non-zero eigenvalues should be also be the eigenvalues of the other reduced density matrix, that is row 2, which cannot happen. So the dimensionality of the smaller subsystem actually one has to take into account. That's why this lowest integer of n over 2 is taken over here.
Oh, okay. Okay, got it.
Thanks. Now, as I just described this, on this slide, I just described given an orthogonal Latin square, you can construct such 4-party states. Okay. Now we go back to Euler. Result of Bosch, Shrikande, and Parker, they tell us that you can construct such a state for all dimensions except 2 and 6, right? Because such an arrangement does not exist for local dimension for 2 by 2 case and 6 by 6 case. Okay, and for d equal to 2 for qubits, that's why I gave an example of qubits. For qubits, it's a very surprising result that you cannot find such a state for which all the reduced density matrices are proportional to identity. That is I4 over there. Orthogonal Latin square construction fails because there is no orthogonal Latin square there. But what was shown some 2 decades ago was that there is no such state of 4 qubits, which is absolutely maximally entangled. That means the reduced density matrices are all proportional to identity. And this result is actually now understood using different different ways. For example, there are some bounds on this paper on these bounds on AME states, the existence bounds on the existence of AME states and all that rule out the existence of AME of n comma 2. Okay, n is 4, sorry, 4 comma 2. So 4 comma 2 was known that it does not exist. Okay. Now the only case which was remaining was the AME state of 4 comma 6. Okay. So that's exactly what I have sort of summarized over here. And the question which I'm just saying it qualitatively, what the question, the inputs which we take are the following. The first input we take are actually the all quantum Latin squares cannot be obtained from classical Latin squares. So there are some genuinely quantum, what are called genuinely quantum Latin squares, which cannot be obtained from a classical Latin square. In some sense, intuitively you can think of the classical case as a very extreme case of a quantum in which you just have one orthonormal basis. But you can, when I was defining those, for example, over here, you can just say, there's nothing much in terms of orthonormal basis because you just have one orthonormal basis over here. Because, for example, if I look at this row, this is the same orthonormal basis which is over here. These are just a different permutation of the same basis states. But what can happen is actually you can have an altogether different basis over here. You can have an altogether different basis in some other dimensions. And what's known is actually that such quantum Latin squares are called genuinely quantum. They exist only for dimension d greater than or equal to 4. So for d less than 4 or d less than or equal to 3, all Latin squares are in some sense, so there is a notion of equivalence and all, they're in some sense equivalent to the classical construction. And similarly, there are also, since our interest is in actually in the local dimension 6, d equal to 6, and in d equal to 6, we can have these, let's say, orthogonal quantum Latin squares, which you cannot obtain from the classical orthogonal Latin squares. Okay, so the question which we asked nearly 3 years ago was that, can there be construction of AME states beyond the classical OLS? That means, is there some quantum construction, okay, of these AME states? Or, to be put it more precisely, does AME 4-6 state? That means AME state of 4 6-level systems. Okay, n is 4 is number of parties, number of qubits or whatever. D is the local dimension, that is 6 level. So you have to think of these four parties A, B, C, and D, let's say. And each of them have local dimension 6. Each of them have six level systems. And what you want is you want to get a state such that if you take the reduced density matrix of any of them, it should be proportional to IF36. Okay, or to put it on the other way, once you find an AME state or the orthogonal quantum Latin square of size 6, because we know that all of them cannot be obtained from this one. So this one we know it does not exist in d equal to 6. But this does not rule out the existence of orthogonal quantum Latin squares, which cannot be obtained from this one. So in some sense, this will provide a solution to this 36 officers problem in the quantum case. Okay, in a manner I'll make it more precise. So what we were trying to sort of do is, sorry for going back and forth, but let me just make it more clear. What we want to do is, so we have an arrangement like this in the classical case, then we go into the quantum. Okay, the thing is, for d equal to 6, we don't have something like this such that we can go over this. But the existence, non-existence of this does not exist, does not rule out the existence of some more general sort of object where you can have entanglement and superposition, okay, which cannot be obtained from the former, from the classical case. That's exactly what we mean by this finding the solution in the d equal to 6, whether the 36 officers problem has a quantum solution. So And what we did in this work, which I'll mention in the rest of my talk, is actually we found that an orthogonal quantum Latin square of size 6 exists, and the 36 officers problem has a quantum solution. So there's some question. I have a question regarding 36 officers problem comes under combinatorial optimization problem. If yes, throw hybrid. Thank you very much for this question, and I'll actually in the rest of, in a couple of slides, I'll actually put it as an optimization problem, essentially.
Suhail, would you mind repeating it out loud just for the people at home watching on YouTube?
Sorry.
Could you repeat the question out loud just for the people watching?
Oh, sure. So the question is, okay, yeah. Thank you very much. So question is, I have a question. The 36 officers problem comes under combinatorial optimization problem, if I am right. Can it be solved through variational hybrid algorithms in quantum case? So this is a question from Abdullah K. And what I was saying is actually I'll describe the solution in a couple of slides, which in some sense can be viewed as an optimization problem. Okay, so what we found is actually the orthogonal quantum Latin square of size 6 exists. That means this AME state of 4 particles, each having 6 levels exist. And let me just describe first what the solution is. I mean, it's not a simple solution to sort of, it's not as simple as a orthogonal Latin square in the classical case in the following sense. So shown over here, let me just sort of first describe what the solution is, and then I'll go to the details, how we found this solution. Shown over here is a 6 by 6 arrangement. So there are these 6 rectangles. You can see 1, 2, 3, 4, 5, and 6. Okay, 6 by 6 arrangement shown over here. And in each 6 by 6 arrangement, you have actually either 2 cards. This shown over in terms of ket, because we are thinking in terms of quantum states now. So you have either 2 cards in each of these 6 by 6 arrangement. You either have 2 cards or you have these 4 cards, okay, shown over here. So the cards are ranked from, so we have ace, king, queen, jack, and then there are these 2 ranks, 10 and 9, or I don't know what scheme of cards which we have used, but these are the, this is how we label the 6 different, these ranks, ace, king, queen, jack, and then we have 10 and 9. And you can see what's important is actually in each this cell, there are 2 cards, or either 2 cards or 4 cards, okay? And they appear in this funny composition, funny way, in the sense. So by this, I mean, I have a ket ace of this clubs and the king of spades, this one. So that means this is actually a superposition of these 2 cards. Okay. Once it's a superposition, that means it is an entangled state over here. Okay. Each of this cell actually describes an entangled state where either you have 2 amplitudes or 2 coefficients, or you have 4 coefficients. Okay. Over here. And the one of the things you can see is whenever there is an ace and king, for example, ace and king is over here, and you have these clubs and spades, and the other combinations where they appear are over here, for example, and over here. Okay, so they kind of group in these cliques over here. I mean, there is the way they kind of get entangled, these ranks and regiments, in a very peculiar case, as we have described it in the paper also, in order to result in this arrangement. Now you can ask me how do we get to this final combinatorial design? Because I'm just giving you the sort of the underlying design of this, because I'm not giving you the coefficients. I just told you it's an entangled state, but you might ask me how much entanglement is there, what are the coefficients and all. Actually, when you take the combination of these 2 cards, you will actually have it, some of the cells contain the complex numbers also, okay, as I'll briefly mention. So the underlying so what I mean over here is this is an orthogonal quantum Latin square of size 6. If you take any cell and take the inner product with other cards, I mean, if one is not compatible with these ranks and suits, you can translate them to numbers from 1 to 6, for example. And I believe that in one of our recent works, we have done that. And you can translate into the 1 to 6, then see that all these 36 entangled states, okay? So these are 36 shown over here are actually 36 entangled states, and they're entangled in a very peculiar way. In this, as I was describing, these aces and spades are getting entangled. Similarly, aces and diamonds are getting entangled and all, okay? Ace, diamond, king, and heart, you can see over here, ace, diamond, king, and heart. So they're getting entangled in these cliques of officers.
I have a question, like.
Sure, please. I expect a lot of questions on this slide because this is something very, very non-trivial. Yeah.
So I want to ask, like, what is the point of this arrangement, like diagonal of diagonal?
Okay. So I wish I could write, but Akash, you can just think of this as a 2-qubit system. So the 0, 0 coefficient is 0. Then you have 0, 1 is non-zero, 1, 0 is non-zero, and 1, 1 is 0. Is that clear? So
I see. Okay.
So you have to think each of these as 2-qubit status, where either this empty over here, the first one being empty means that coefficient is 0, but this coefficient is 0, 1 coefficient is non-zero. Similarly, 1, 0 is non-zero and 1, 1 is 0. For example, in this one, all 4 coefficients are non-zero. Okay?
Okay.
This one just as diagonal entries. Okay, so this is an orthogonal quantum Latin square of size 6, and this arrangement you cannot obtain from any, because there is no classical case, and because it has entanglement in it, it is a quantum solution to the 36 officers problem. Okay, so thinking in terms of this ace, king, queen, you can think of this as the regiments of this, regiments of those officers, and then you have suits of officers, and what you allow is actually now the entanglement between these ranks and regiments. They get entangled in these peculiar ways, such that now the way you check about the fact that it is an orthogonal quantum Latin square is you construct the 4-party state, right? So if you construct the 4-party state out of these 6-level systems, the reduced density matrices, all 3, what are those partitions I was talking about, all 3 of them are maximally mixed. Okay. Now, how do you come to such a, such a non-trivial combination?
Well, one doubt. So, like, although there are 6 suits, I see that here you use 3 colors, right?
Okay.
Actually, significance of that, or would it have been better if there were 6 colors?
Maybe, but actually, the way these cards are getting grouped together, I would just have, how many colors are there? 3. I mean, in terms of that, I should have 4 colors only. But I mean, it's just for making it a bit aesthetic. There is no such information encoded into the colors, I would say.
Right. But in the, I guess earlier in the case of 3, could think like that.
Yeah.
So coloring in the classical case.
We have used some color-coded things in a follow-up work where some information is encoded into the color also. But I think there the color we have used it in the in the background color.
I see.
Somewhere in some we have done that. But as over here in this picture, I mean, there's no information encoded into the.
Right.
Okay. I think, Akash, how much time do I have? Sorry for bothering again and again.
Yeah, I think you have something like not too much, maybe 5 minutes.
5 minutes. I think I should be perfectly fine. Let me just, in the remaining of the talk, get a bit more technical as I had promised, and see whether we can understand such a construction of such 4-party states. And the idea which I use is maybe familiar to many people because it appears in different contexts, is called this operator state isomorphism, or sometimes called the Choi-Yamyovsky isomorphism. And the idea is simple. You consider any bipartite operator. I'll denote it by U because for us, the objects which will, the operators which will be useful are the unitary operators. So we take any bipartite operator on this Hilbert space. That means it is a d square by d square matrix. So you have to think like that. Take a d square by d square matrix. I can construct a four-party state. That means a four-party state psi of U, which is given, let's say if I have a product basis, which is the usual computational basis, I can construct a state out of this unitary operator like this. So all the coefficients of all the amplitudes of the state are actually encoded or come from the unitary operator U using this mapping. And I can write it in the form shown on the right hand side, which is not, let me not get into that. But the question is the following, but the idea is the following: you have a d square by d square matrix, then you construct a state out of it using this flattening mapping or something. And the question which we ask is the following. Suppose we have such a, by the way, shown over here is an operator UAB IAC. So U acts on A and B, and C, U acts on operator A and B, and A is maximally entangled with C, B is maximally entangled with D, which is shown over here. Okay, so A is maximally entangled, shown using this wiggly line over here. A is maximally entangled with C, B is maximally entangled with D, and a unitary operator U acts on A and B. Okay. Now, the first question we ask is the reduced density matrix corresponding to partition AB versus CD. Once you write a state like in this form, then it is not hard to see that the reduced density matrix corresponding to AB versus CD partition is given by UU dagger. Okay. Now, the second partition is AC versus BD. Okay, so second partition is AC versus BD, and you can show that the reduced density matrix is given by a rearrangement of U. Okay, so you have to take a rearrangement of U called the realignment, which is shown over here. So the realignment is defined like this in product basis. So you have these matrix elements N beta alpha, M alpha, N beta. Then you interchange these two indices, okay, corresponding to the second subsystem and first subsystem, which are shown over here, such that you group the Latin indices on the left and right, Greek indices on the right hand side. So this is called a realignment operation. So this is the reduced density matrix corresponding to second partition. And the third partition shown over here is BC versus AD, is given by the one more rearrangement of U called the partial transpose. And let me just emphasize, these are the same matrix arrangements which come in the separability criteria of mixed states. Okay, and they naturally arise in the context of this multipartite entanglement. So let me just revise. I start with a unitary operator U, then flatten it, which I can write like this. Then I need reduced density. Then I calculate the reduced density matrix of AB, AC, and BD. Okay, BC. Sorry, and these are determined by U, UR, and U gamma. And what I need is for this AME state, I need that all these reduced density matrices should be maximally entangled. That means for maximal entanglement, what I need is rho AB, rho AC, and rho BC should all be proportional to identity. That means identity divided by D square. Okay, that means I should have a unitary operator U, which remains unitary under R and remains unitary under gamma. And if you take a general unitary operator, do this crazy reshuffling and partial transpose, in general, it's not going to respect unitarity with respect to these linear operations. And this motivated the definition of what's called a two unitary. Okay, it's known in different. It's been given different names to different by different communities. So for we usually call it two unitary. So a two unitary operator U is a bipartite operator which remains unitary under this R and gamma. That means UR and U gamma are also unitary. So this was introduced in this work in 2015. So the existence of four-party AME status now boils down to finding a unitary operator which remains unitary under R and gamma. Okay, and based on this, you start with first the case of, so you can sort of you can construct these. You can pose the question of existence of AME states of 4 particles using the existence of these, whether such operators exist which remain unitary under partial transpose and R. For 2-qubit case, it's actually very easy to show that such constraints cannot be satisfied for a 4x4 matrix. That means if you have a 4x4 unitary matrix, then you impose these constraints over here. It seems too much for a 4x4 matrix to satisfy all these constraints. Hence, there is no 2 unitary, and as I was saying, there is no AME state of 4 qubits. Now, the interesting case for us was how to find such unitary operators which remain unitary. So the method which we used in our paper, which we had introduced in an earlier work, is called a dynamical map for 2 unitaries, and the way it works is the following. So suppose you take a random unitary, okay, random unitary numerically, for example, you generate a unitary matrix, you do a realignment of this, which I denote by U0R. In general, it's not going to be unitary. Let's try to do one more rearrangement, the partial transpose. So I do a partial transpose of this, I get a matrix out of it, which is U0 gamma. It is still a d square by d square matrix, but in general, it won't be unitary if I start with a random unitary, for example. Now, I take a very crucial step, which was known in the literature. I project this matrix, which is not unitary, to the closest unitary matrix, which is given by its polar decomposition or the singular value decomposition. So I obtain the closest unitary matrix to U0 gamma R, which is given by polar decomposition, and put it and project it to U1. Now for U1, I do the iterative map. I do this procedure iteratively. And what I expect is U gamma 2 unitary? At the end of the, I mean, if I do it, I mean, in practice, we do it for finite number of iterations. And what we expect is U infinity, thus this procedure leads to 2 unitaries. And to cut the long story short, how we solved this problem for d equal to 6 is shown qualitatively in this figure over here. For the purposes of this talk, I mean, you can just forget about what is on the y-axis, but focus on the x-axis. So on x-axis, there is something called entangling power. And there are 2 lines which I want you to focus because I have introduced them. So there is a line which is shown that U gamma belongs to U36. So those operators for which remain unitary under partial transpose lie on this purple line. Okay, and those operators which remain unitary under realignment lie on this line. I mean, they have been given different names, for example, dual unitary, or in the mathematics literature, they are called biunitaries. So we have these 2 lines. These special operators lie on this on these boundaries, and what we are interested is actually on the intersection of these 2, because on the intersection is the point where these 2 unitaries lie, where the unitary operators which remain unitary both under realignment and partial transpose lie. Okay, and we are interested in this one. So what we did was we started with some very special U0, which is shown over here by PS, and ran this algorithm. Okay, we ran this algorithm. We took some complex perturbation of this. We ran this algorithm. You can see that 2 trajectories actually shown in red go to this point AS. That means they don't reach the this EP equal to 1. So you can EP equal to 1, but the green one actually leads to this one. So let me just try to connect it to one of the questions which was asked, whether this can be viewed as some sort of optimization. So you can think of this problem as an optimization problem for maximizing this what we call an entangling power, which is determined by the singular values of UR and U gamma. So you can think of this finding the problem of such structure, I mean these special unitary operators, as an optimization problem for maximizing entangling power. And what we have shown this algorithm. What it does is, in some sense, what it does is it actually some perturbations are actually able to avoid these local minima, like shown over here as A and A times S, and there is some other local minima also W. Somehow this complex perturbation shown in green over here, in some sense, it avoids these local minima, finds a mountain pass, and reaches to the 2 unitary point U36. Okay, and this was the first numerical evidence that sort of encouraged us to find such a state. And then what we did was using some, techniques from this minimization techniques from the literature. It was sort of minimizing some entropies and all to construct to obtain some simpler state. And what we showed is actually the 2 unitary of size 36 actually exists, and the 2 unitary which we have given in the paper is a 36 by 36 matrix, which is shown over here. The absolute values are shown over here. This is the analytical form which we have obtained. It's not the one which we have found numerically. It was derived from the numerical matrix which we found from the algorithm, and the analytical form has this analytical matrix has this form. So you can see it's a 36 by 36 matrix, and to connect it to the design which I was showing, you can see that each row shown over here, each row has either 2 elements or 4 elements. Okay, you can see it over here, shown over here, and the each row has 2 or 4 non-zero elements, and most importantly, all the amplitudes. So there are out of so if you have a 36 by 36 matrix, you will have 1 to 96 non-zero elements, but there are only 112 non-zero elements in this matrix. And quite remarkably, all the 112 non-zero elements, the absolute values are given by these blue, red, and delta square, and these are the algebraic, the exact expressions for these numbers, 1 over square root 2, and these combinations over here. And interestingly, if you divide the green one divided by the red one, you get the golden ratio. Okay, and we have doubled this as the golden EME46 state. And this matrix, okay, this matrix from which the that design which I showed, that design which is essentially built from this one, is actually the quantum solution. If you think the 36 officers problem in the quantum case provides a quantum solution to the 36 officers problem. Now you can ask me, how do you know that this matrix satisfies the unitarity with respect to R and gamma? So what is done over here is actually what we have found is a structure. Okay, what we have found is a structure of this matrix which remains invariant under R and gamma operations, so that if you do this arrangement, in some sense, it does not, the form of this matrix does not change, and it leads to this 2 unitary matrix. I think I had some trouble with the compilation. Let me just stop share. Okay, let me just take the question first. Sorry if I missed what is on the y-axis. Okay, the y-axis is entangling power. So it is some sort of maximization function which is maximum only if it is a 2 unitary. Okay.
I meant the GT of U.
Oh, it's a gate typicality, but it's just the thing that this GT of U, when it is half, you can see over here, it leads to 2 unitaries, and EP is 1. So EP has to be 1, GT has to be half. So these are some sort of quantities which you want to, which is the target for your algorithm. When it hits this one, that means you have converged it to a 2 unity. It's called a gate typicality.
I see.
Yeah, and this one is the entangling power. And both of them are actually determined by the singular values of U gamma and UR. So actually I had some couple of slides over here, but unfortunately I had some trouble in the compilation over here. But this is essentially the idea, and the two unitary matrix which is shown over here, the design is actually followed from this one. So you can see if you take the first one, it just has let me just sort of do it in a more detailed way. If I take the first 4 columns, first 4 rows, 1, 2, 3, and 4, you can see the first 2 has just the amplitudes 1 over square root 2 and 1 over square root 2. The other have 4 non-zero elements determined by this one, and these are the same, the design which you can see over here. The first 2 are just 2 non-zero elements, and you can see that they have the same font size. But if you look at this one, for example, the font size has been taken different because of the amplitude. Okay, and you can see the font size over here are the same because the amplitudes are the same, and they have 4 non-zero elements. So this design is constructed from this 2 unitary matrix. I'm extremely sorry. There are some conclusion slide and all which I had trouble in concluding, but I'm happy to take the questions now.
Yeah, thanks for the amazing talk. And I have one question, like in the end, why did you show the golden ratio? Like what is the point? Like,
sorry?
Like in the end, you show the golden ratio, right? Like
right.
The point? Like, I mean, is there any?
No, the thing is, actually, I mean, you might ask me, why did the golden ratio appear in your calculation? The only thing I can say is the way we constructed this state and all, it automatically came into the construction, right? I mean, there may be some underlying symmetry of the state, which is not known to us presently, which kind of enforces such a universal sort of constant to appear in the construction of this state.
I see. Okay.
I mean, there may be some sort of symmetry in the solution, because of which this is. We have actually used it in the proof of showing that we get an Rayleigh's quantum solution and all. But this is something which is quite surprising, actually, that this golden ratio appears there.
Yeah, it's really interesting. Thanks for the talk again. And if anyone have any questions, then you can unmute yourself and ask.
Sure.
Sure, I have another question. So these Latin squares are d by d. Is that correct?
Which Latin squares are you?
Well, when you try and like solve, let's say the 36 officer problem,
okay.
Like a 6 by 6, right?
So So what is I have described this as a, I mean, quantum solution over here. So what is quantum about it is the first thing to distinguish it from the classical case is that each cell has a 2-qubit state. That is the case with the classical orthogonal Latin square also. But the distinctive feature of this is actually there is an entanglement over here, which you don't have in the classical case. And because you have entanglement, you can no longer separate into 2 quantum Latin squares. Okay, and or you can think in terms of, let's just forget about everything. Suppose I'm interested in finding a basis in d square dimensions. I can find a product basis in d square dimensions, right? But I can also have an entangled basis. And this one is actually an entangled basis with an underlying structure of an OLS. Okay, so this one is, although this is a 6 by 6 square arrangement, you can no longer separate it into 2 quantum Latin squares because of the entanglement. And
sure,
we don't have problem over here because you don't have entanglement over here, right? In the classical case, we can just factor it into 2 and all that. And over here, I mean, since you have asked this question, if you have to really look at the properties, what you have to take is the reduced density matrix of each of the subsystem in each cell. And when you take the reduced density matrices of each of the subsystem, then they are no longer pure state because it is entangled. Then they satisfy some constraints of orthonormality and all, which are in the literature sometimes called some magic unitary conditions and all. So, I mean, in a more, technical language, what's happening is actually you are extending the algebra or non-commutative. You are making your algebra to non-commutative entries. That means you are going from these projectors to general POVMs. Or, I mean, to make it, sort of easier is that you start, so my construction was like this. I started with a symbol. It went to a vector. And then what's actually done over here is actually there are constraints which involve matrices now. So we have went from this commutative sort of thing to a non-commutative algebra over here.
Makes sense. And
yeah.
so in this case, I mean, you essentially have two particles with these two states, right? And so
exactly.
and classically maybe that's just the same thing, but you cannot have entangled states. And have people thought of whether classically or quantumly a more generalized version of this problem where you could have like d times d times d, so now suddenly you have it in like 3 dimensions, and then
okay. So people have actually this work is actually appeared over here in this PRL. It was actually communicated in the spring of 2021, and it was published in PRL nearly a year ago. And this was in collaboration with Adam, Wojtek, and Grzegorz, who were then PhD students of Carol. And now they have moved to different places. For example, I think Adam is at QSoft, Wojtek is in Polish Academy of Sciences, Grzegorz is in ICFO, Spain, and Arul is my PhD supervisor, who is still at IIT Madras, where I did my PhD. Sorry, what your question was?
It was about the generalization, and if there were people thought of generalizations to make it.
Oh, yeah. Okay. Yeah. Sorry. That's how I sort of view the time. Thank you very much for reminding me about my collaborator. So, and actually, if you look at some of, recent works of Carol, so they have generalized this notion. So there is quantum Latin square. Now you can think in terms of 3-dimensional array, which is quantum Latin hypercube. Okay, quantum Latin cube. Okay, so what you will have repetitions along row, column, and then you will have a third dimension where you will not have repetitions. So there are these generalizations, higher dimensional generalizations of orthogonal Latin squares called orthogonal Latin cubes and hypercubes also. And this is work by Carol and collaborators. Interestingly, there you will have 6-party AME states. From 4, you go to 6 to 8 and all, like that. Did I answer your question, or I said something random?
No, I mean, it was answered. I mean, like, I wondered if there was any like.
Yeah, there is a higher dimensional because it's sometimes confused higher dimensional because we have dimension of Hilbert space.
Right. So not the dimension of each particle,
there is a number of particles. Yeah, number of particles. For example, for 6 particles, you want an AME state and all. For example, for 4 qubits, it does not exist, but for 6 qubits, it exists. For 6 qubits, an AME state exists, and similarly for 7 qubits and all. And you can construct. There are analogs of quantum Latin squares in terms of quantum Latin cubes and quantum Latin hypercubes also. But there is a generalization. Yeah.
Thank you.
Yeah. Okay.
Okay, thanks. So I will just stop the recording right now.
Yeah.